In today's video, I'm going through exercise 1.19 from the Art of Electronics. This exercise is about inductors and turn ratio. So I will be going through the solution first and then explaining a bit more about inductors with a simulation. So let's get started.
So excited!
For exercise 1.19, we need to explain why the inductance is proportional to the number of turns squared. And it basically asks us to consider a coil of n turns of wire with a fixed diameter and length. So we'll have some constants with a fixed value of diameter and a fixed value of length. We need to basically vary n and show the relationship of inductance is proportional to the number of turns squared. So this exercise, there are a lot of equations, so I think it's useful just to look at the different variables that are involved in coming to the solution. So the first easy one is L, which is inductance, and it is measured in henries. The second one, H, which we don't really use for the solution but is still useful to know, is the magnetic field strength, and that is amps per meter. The third one, phi, is the magnetic flux and it's measured in Webers. Another symbol is B, which denotes magnetic flux density and it's Webers per meter squared. Then we have capital N, which is the number of turns, A for area, which should be meters squared. I'll fix that in edit. And mu is the permeability of the magnetic material, which has two different SI units, so it can be henries per meter or newtons per amp squared. So let's first start by looking at the self-inductance of a coil. This is given by equation 1 on the screen now. Inductance is equal to the number of turns multiplied by magnetic flux divided by the current. At this point, I think it might be useful to read up on Lenz's law. I won't be going through that in detail here, as I just want to cover the solution for the question. The inductance of a coil also depends on the characteristics of its construction. Obviously, we know for the question the diameter and length is fixed, so that does influence the inductance, and also the magnetic properties of the core. But the magnetic flux is equal to the magnetic flux density times by the area of each turn, and I've denoted that as equation 2. We can substitute equation 2 into equation 1 and get the following. So what we are doing is basically replacing this symbol here with this part. So we get inductance is equal to the number of turns times by B times by A divided by the current. If we assume a uniform magnetic field density, then the magnetic flux density through a coil is equal to mu times H, or number of turns times mu multiplied by the current divided by the length. If we substitute this B into this equation here, so we're substituting equation 4 into equation 3, so replacing this B with N times mu times I divided by L, we get the following equation. So we get our N squared relationship that we're looking for, multiplied by the current, which we have from here, times mu times A. Now the currents will cancel each other out and we end up with this equation here. Now we know the dimensions of the inductor coil are fixed in this question. So A, L and mu, which is the magnetic property of the core material, they're all fixed, so we can assume that to be a constant. So if we denote that as A, we can show that the inductance of a coil is equal to a constant times the number of turns squared. And that is the solution to this question. As I haven't covered inductors on this channel before, I'm just going to go through some basics and show you how they work with the simulation. If you understand capacitors, I think inductors are fairly simple to understand in how they work. So capacitors obviously store their energy in the form of electrostatic potential energy, whereas inductors store energy in the form of their magnetic field. So in a coil, when the current flowing through it is changed, a magnetic field gets produced. The magnetic field induces a voltage in the coil, which tries to attempt to oppose that change in current. And that's what's known as inductance, basically. Now, the higher the inductance of a coil or a part, the more the coil will resist the change. And this, you might know the equation VL. So the voltage across an inductor is equal to L, the inductance itself, times by the change in current, which we can write down with this. So VL is equal to DL times di by dt. So all this equation says is that when you have a large change in current with a fixed inductor value, you're going to have a large change of voltage, or you're going to have a large voltage drop across the inductor. Now let's consider two different circuits. So I'm going to put down a power source. So I've pressed F2 to bring up select components. So voltage source, and then if you press F3, you can place wires on the LT spice. I'm just going to create a basic circuit with a ground referenced here. Now for inductor, the shortcut is L, and to rotate it is Control R. I've got an inductor, then I'm going to put down a load resistor, and the shortcut for a resistor is the letter R on your keyboard. So let's say we have a 1K resistor. If you right click on the symbol, you can change the properties. And let's say we have a 1 microhenry inductor. Now if we pass a DC value through this circuit, so we have 1 volt DC being applied to the circuit, you'll see that the voltage across the resistor is almost the same as the input voltage. So the green line is the input voltage. At this point, I think it can be useful to add in some net labels. So I'll put my power supply here, so voltage source, and output voltage here. I'm going to call this Vout1. So that's your Vs and that's your Vout. And you can see there's very little difference between the two. The difference mainly comes from the ohmic resistance of the inductor itself. And you can see the current through this is 1 milliamp, or approximately 1 milliamp. Now let's see what happens if we introduce a AC current. So a voltage source which has a change in current. So for the first part of the circuit, our di by dt value is equal to 0, as our current is not changing. So if the di by dt value is 0, that means that all of this is 0. That means the voltage across the inductor in an ideal case would also be equal to 0. Now if we increase the rate of change of current by adding a AC source, we can induce some voltage across the inductor. So let's try this with two different frequencies. So what I'm going to do now is right click on the power source, click on the advanced button, and then add a sine wave. So let's first of all start with a low frequency sine wave of 10 Hz and see what happens. I've changed the net labels to VAC, low frequency sine wave, and Vout2. So we can see our, well, we need to change the simulation time as the frequency is very low. What I'm going to do is increase the frequency a little bit so that we get a full cycle. So now you can see we've got 3 cycles on this diagram. So if you look at V2 and V1, there will be very little difference between the two as the frequency is still very low. So what we're saying now is the di by dt is a small value. Now a small value of inductance times by a small value of change of current will get a small amount of voltage drop across the inductor, which we can see by checking the voltage drop across the inductor by itself. So you can see we've dropped some of the voltage on the inductor, roughly 80 microvolts. So now let's see what happens if we increase the frequency. And I'm going to call this Vout3. So now we have a new circuit with the input voltage being VAC high and the output voltage is Vout3. So we still got our 1 volt input signal and we've got our roughly 1 volt output signal. But now if we look at the voltage drop across the inductor, you'll see that it will be higher than what it was previously. So what happened there is the maximum step size was 2. You can see we are now applying 1 volt 3000 hertz sine wave to this circuit and the output still looks roughly the same. But now if we check the voltage drop across the inductor, that should be a lot higher. So you can see the voltage has changed to about 20 microvolts, whereas the voltage drop across this circuit was lower as the frequency was smaller. I'm just going to rename this. So what I'm going to do now is simulate the circuit with a very high frequency where we get substantial amount of voltage drop across the inductor. So let's try 300 megahertz. For this I will need to reduce the simulation time. So let's say roughly 5 microseconds with a step of maybe 1 nano. Let's see how that works. I forgot to change the names on this, so let's say change this to VAC high and V output 4. So now we have a very high frequency signal going in, 1 volt still, and we can look at the output voltage and it's starting to look a little bit different now. If we look at the voltage drop across the inductor, we can see that it's gone a lot higher compared to when for the lower frequencies. So the point I'm trying to make is that the inductor's voltage drop is dependent on the frequency that you apply. So as opposed to resistors where the voltage drop is independent of frequency in an ideal case. So inductors can be very useful to limit noise and things in your circuit. So typically you'd use an inductor between your microcontroller power lines and your analog power lines. And what this will do is, if you have a very high frequency signal, let's say in the range of megahertz, the frequency will be attenuated or reduced in size, and you'll basically see less noise on the analog side. If you have any questions, please let me know in the comment section below. Thank you for watching.